here. All right. So this is going to be instantaneous. Rates of change. Rates of change. And this is the second big topic in AP Calculus. Our second big topic, instantaneous rates of change, and what this means. Instantaneous rates of change. So let's define some pieces here. What does it mean by rate of change? Rate of change. What is a rate of change? The sort of definition, or the sort of, just like just the meaning behind what we say when we say rate of change. What is it we're talking about? A rate of change is simply, it's basically a slope. Basically a slope. It's like a change over time. It's a change amount over time. It can be over time, or it's when something changes compared to something else. One change compared to another. Some examples of rates of change are things like speed. Right? Speed is distance over time. That's a rate of change. It's a rate of increase, of distance per unit time. That is a rate of change. It's how much your position changes in time. Right? Or you could be filling a bucket. Filling a bucket. Could be a rate of change. It's the amount of water per the amount of time in the bucket. How much water is in the bucket over a certain amount of time. It's a rate. And rate means like something could be increasing or decreasing. A rate is an amount of change. A rate of change. It's basically a slope. You're talking about slope, right? How much the rise over run is. A slope, which is rise over run. And that is a type of rate of change. How much something goes up and down versus how much something goes across, right? That's a rate of change. It's one change compared to another. A change in distance over a change in time. A change in water over a change in time. Sometimes it can be, it's one change compared to another is the third bullet point. One change compared to another. Rate of distance, right? Change in distance over change in time. Change in water over change in time. It can be even something like not having to do anything with time at all. It can be maybe, what's a good example? Maybe something like, you can do your height per, like you're changing height. You're growing. Your change in height over the years that you've grown, right? What is your height over the various years, right? Whatever the change is, whatever the amount of change, right? It's always a comparison. Always, it's like a slope. Rate of change, rate of something over rate of something. Water over time, height over years. You can even have rates of change for like volume is another example, right? Volume, like of a sphere or a cube, right? If you have a sphere, It's the volume compared to the radius. Radius of your sphere, right? This is your radius of your sphere. So the volume changes with the radius. You can consider that to be like a rate, right? How much does the volume change of a sphere depending on how much you increase your radius? That can be a rate of change. How quickly it's going up and down, right? What's the volume over radius? Any kind of thing where you compare things, something over something, a change over a change is a rate. Typically like distance, filling buckets, these kinds of things we talk about. Volume sometimes happens too, rate of change, right? It's an amount of change over another amount of change. One change over another. And so we talk about a couple different types of rates of change. We can talk about a few different types of rates of change. What we mean by average rate of change, average rate of change. An average rate of change is the total change divided by the total, let's say, for example, time. An average rate of change is the rate, I should say the amount of change from the beginning, goodness gracious, from beginning to the end. An average rate of change is an amount of change from the beginning of something to the end of something. Average rate of change is you have a starting point, you have an ending point. How much did your change? How much did this change over that period of time, for example? So an average rate of change is, for example, your average speed of a drive. Right? How long it took you, right? It would be the total distance, divided by the total time it took you, total time. Let's say you drove for 2 hours, you went 500 miles. That's 200. That'd be a little bit too much. 50 miles over 2 hours, average of 20 miles an hour, 25 miles an hour. 50 miles over 2 hours, average of 25 miles an hour. Sometimes maybe you were stuck, you were going over that speed, right? But your average speed over the course of the whole distance is your average rate of change. Right? So it's from the beginning to the end. It doesn't care what happens in the middle. It's just what happened, where did you start, where did you end? Or for example, let's say your average growth rate of maybe like a plant, right? You take the total change in height divided by the change in time. How much did the plant grow in this period of time from beginning to end? The change from the beginning, some beginning point to some ending point, your average rate of change. And so the formula for your average rate of change is like the formula for slope. Again, this is like we're finding a slope. equals rise over run, like a slope. So your formula, average rate of change, I'm going to call it ROC, rate of change, is how can I say this? The ending value minus the start value divided by the ending time minus the starting time. In a formula, this would be f of b minus f of a over b minus a, which is exactly the slope formula, which is like y2 minus y1, right, your y's, over x2 minus x1. This is like your slope formula. Same thing. These a and b, this is your x values, and the f of a and f of b, these are your y values. Ending value minus the starting value over the ending time minus starting time, right? Your rate of change. Your slope, same thing as you've been doing since 8th grade. But now we're kind of giving it a context. We're giving it some information, some placement. This is your average rate of change. F of b minus f of a over b minus a. This is our formula for rate of change. Oh, goodness gracious. There we go. All right. So let's talk about an example. So let's say it takes let's see, where are we going, everybody? Pick a place that we're going to. I don't know where we're going these days. I'm not going to school. I was going to say it takes 20 minutes to walk to school. The mall, sure. It takes 20 minutes to walk to the mall. That is 3 miles away. What is your average speed or average rate of change on this walk? Sure, that could be a walk. Why not? 2 hours? No. 20 minutes? Well, okay, fine. Maybe more than 20 minutes. Say, what, hour and a half? 90 minutes? 90-minute walk? Sure. Doesn't matter the time. Let's just use your imagination. Whatever, 20 minutes, 90 minutes, doesn't matter. So, if this is our situation, 90 minutes to walk 3 miles, what is our average speed on this walk? Our average rate of change. Right, our rate of change could be equal to, we would say, well, the distance divided by the time. Right, exactly. We would have, well, no, other way around, Lizette. We'd have our distance divided by time, right? 3 miles. We walked 3 miles in 90 minutes. Or we could say, so that's going to be what? 3 divided by 90, that's about 0.03 miles per minute. And here's an important thing you need to remember. Always use units. When you're dealing with these rates of change problems, it's always going to be about something. They'll always be about a situation. And so you need to use your units. You always need to explain what it is you're talking about. 0.03 what? Right? We could also do this in miles per hour. Right? We could say, okay, instead of 3 miles in 90 minutes, I could say this is 3 miles over 1.5 hours. Right? 3 miles in 1.5 hours, which would be a different thing, right? Different number. So that would be an average of 2 miles per hour. And so these answers are both correct. Both these numbers are correct, right? It just depends on the units. That's why having the units is so important, to know that if you just put 0.03, I'm not going to know, is that the miles per hour that you're using? Because that's not correct for miles per hour. Right? This is not correct for miles per hour. It's correct for miles per minute, but you need to label it. If you write 2, I'm going to think, well, is it 2 miles per minute? Well, that's not right, but it is right for 2 miles an hour. So label your units, make sure you know what it is we're talking about. Right? What it is we're talking about. So we can figure out our average rate of change of a situation, right? Our total distance divided by time. Always use your units. That way I know that what you're talking about is correct. Again, both of these are right because I have the units explaining what it is that we're doing. Right? One was in minutes, one was in hours. Make sure our situations are correct. Oftentimes, however, we're not going to be given the data like this. I mean, sometimes we are, but sometimes we have to use some formulas. For example, let's say in the equation y equals 2x squared plus 3x minus 1, what is the average rate of change on the interval (1 to 4). So sometimes your questions will be posed like this. So now we're given a formula, we're given an equation, and we want to know what is the average rate of change on this equation from starting from 1 going to 4. So these are my x values. So this is going to be, this is my a, and this is my b. Right? Our starting values, our starting and our ending values. Right? The range we're talking about. We're looking at the average rate of change on a certain beginning to a certain end. So our range is going to be from 1 to 4. So if I use my formula, now I can say, okay, well, the average rate of change, I know the average rate of change is going to equal to f of b minus f of a over b minus a. So what we're looking for is we're looking for the value of the equation. So if I look at this graph, let's say I sketch this graph, it's going to look something like this, okay? something like that. I know that from 1 is right here. That's my A value. Here's 1. This is A. And here's 4. This is my B. I know my ending point is going to be like, I don't know, somewhere over here. So f of A is right here. This is f of A. And over here, this is f of B, right? It's the y values. These y values we're talking about. And so the thing I want is I want to know this line is the average rate of change. This is the slope from A to B. Right? It's the line, the slope of the line that's going from A up to B. And that's what we're looking for when we find an average rate of change. We're looking for this slope, right? My rise over my run. Right? We're looking for the slope between these 2 points. My rise from f of A to f of B, and my run from A to B. How much does the graph go up? How much does the graph go across? Rise over run. So all this formal definition is really just, it's hiding this simple idea. Simple idea of an average rate of change is simply a slope of some graph from some starting point to some ending point. And you've been doing slopes for years and years and years. So you're just doing a slope of this equation, right? Some starting value and some ending value at 4. So to find the slope, I mean, we can just plug this in. I need to know what is f of b, what is my ending value. So I'm going to plug in my 4 to my equation. I'm going to say, hold on, I'm going to say 2 times 4 squared plus 3 times 4 minus 1. That's my f of, that's the first one, right? F of b. Minus that from plugging in the 1. 2 times, I should do the numbers in different colors. Hold on a moment. That 4 and that 4 will be in red. Plug in a 4, plug in. And the same thing, right, for f of b as I do for f of a, plus 3 times 1 minus 1 for the second question, right? So then I plug in a 1 here, and plug in a 1 here, and it's going to be over 4 minus 1. Just do those in blue. Hold on. Over 4 minus 1. Right? My change in the y values, over the change in the x values. I don't need to write it like this. I could do this calculation somewhere over here on the side and just get the number, whatever I need the value of what is f of b, what is my value at 4, plug it in. And then I get my f of a value, plug in the 1 into this equation, plug in the 1 to this equation, get the a value, and find my rise. I'm finding the rise of my equation. This is the rise. This part is the rise. And this part is the run. Right? Run here. And my rise from here to here. Just like you've done for lots of years, just finding your slope. So this is equal to, let's see, 4 squared is 16. 16 times 2 is 32. Plus 12 minus 1. That's going to be 44, 43. 43 minus 2 times 1 is 2, plus 3 minus 1 is 4. Minus 4 over 3. So that's 39 over 3, which is 13. So that is the average rate of change from 1 to 4 of this equation. This equation changes a total of 13 over 1, you could say. 13, right, has a slope. This line has a slope, right? And so this is the slope of the line from A to B. The average rate of change from this starting point to this ending point. That would be the slope. All right? Questions about this? Pretty straightforward. Nothing too crazy, right? Finding a bunch of slopes, plugging in some values. And that is the average rate of change. All right. So if that's the average rate of change, let's talk about our next topic. What is the instantaneous rate of change? Instantaneous rate of change. An instantaneous rate of change is like the speed on your speedometer on the car. On your speedometer. Speedometer. It's your speed, your rate of change at an exact second, at an exact moment. It's like you look at the speedometer and you say, what is my rate of change right now? What is my speed at this exact moment in time? How fast am I growing right at this second? It's your rate of change, your rate at an exact second, an exact moment in time. It's an instantaneous rate of change, right? So you could say something like, say for example, when you drive a car. I don't know how many of you drive. Maybe you're on a scooter. You got, right? You start stopped, right? This is your speed here. And this is your time. And so maybe like, I shouldn't say speed, it's more like distance. Not speed, everyone. This is, I should say, your position. Where you are. You stopped at home. And you drive kind of slowly at first, right? And then you slow down, and then you speed up a whole lot. Maybe you go on the freeway, and then you slow down. Maybe you're at a stop sign. There you go, you're at a stop sign. You go, you're at a stop sign. And then you go a little bit further really slowly, and then you end up where you're going to end up, right? This is a bad drawing. Hold on. Let me try this again. You go really fast, and then really slow for a little bit, and then fast again, stop sign, fast again, stop sign, fast again, stop sign. And you end up over here. Do I like that drawing better? No, I don't like that drawing. Hold on, everyone. Okay, you're going to go backwards. And so you're moving at your speed changes over time. This is the point. Your speed changes over time. Your position is going up and down. An average rate of change, your average rate of change is going to be this one, right? Your average rate of change from beginning to end is going to be like this. Average rate of change. Right? Because you have some starting value, some ending value. Average rate of change. Your instantaneous rate of change rate of change is your speed at some exact moment in time, like right here. It's your speed at that exact moment, and what happens is you have this line just touching one spot on the graph, and this is a tangent line. Tangent to the curve. Instantaneous rate of change is your speed at an exact moment in time. I have manual, yes, about a week ago. Okay, let me try doing this one more time. Let me try this explanation again. Say for example, we have the equation y equals x squared. Okay, your regular parabolic equation. Okay, let me try drawing this a little bit better. You can find the average rate of change from, let's say, 1 to 4. Starting here, ending up here, right, looks like that. But if I want the instantaneous rate of change, instantaneous rate of change at x equals 1, rate of change what I'm going to have to do is I'm going to zoom into this. X squared, y equals x squared. equation's y equals x squared. To get my instantaneous rate of change, what I would zoom in anymore? Oh my gosh. Hold on, everybody. It's too much. I would need to move this point a little bit closer, right? Move my endpoint closer, maybe to here, and then I would get a little bit closer. And then I move it a little bit closer and I get to here, right? If I keep zooming in, right, my lines, right, my graph gets a little bit closer to each point every time, right? I'm getting closer and closer and closer until my points merge into one location, and then I have a tangent graph right at that spot at 1. So my points, what happens is my values of the slope get closer and closer and closer, right? My lines get closer and closer together, my points get closer and closer together until my slope, my change of my x change, my amount of change is so tiny that it disappears entirely. And I end up with a value exactly on the line. Right, my slope is exactly on a single point. And this is your instantaneous rate of change. So here's what we're going to do. How we do this is for the instantaneous rate of change, instantaneous rate of change, what we do is we use the same formula, right? It's f of b minus f of a over b minus a. But what we do is take the limit as x approaches our a value. We take this limit. And this limit means my points get until they meet. And this value is what will give us an instantaneous rate of change, a tangent slope. This is the tangent slope. Tangent slope to a curve. It's basically the slope. Oh my goodness, the slope at a point. The slope of a curve. So you've been able to find slopes of lines, everybody. Y equals mx plus b. But now with calculus, you can find the slope of a curve at a point. How much is that curve? How much is that curve curving? How sharply is it increasing at that exact moment in time? What is the slope at that point? At a single point, not a average slope between A and B, but a slope at a particular value. And to do that, we use this limit equation. we do the limit as a approaches b, as those points get closer together until they are the same value. And that's how we can find an instantaneous rate of change. Let me give you an example. Find the instantaneous rate of change of an equation, y equals, let's say, x squared plus 1. Goodness gracious. X squared plus 1 at x equals 2. It's plus a 1, everybody. Plus 1. X plus 1 at x equals 2. Instantaneous rate of change. Instantaneous rate of change of the equation y equals x squared plus 2 at x equals 2. So if you want to look at the graph, you can imagine like the graph here. Here is our equation, x squared plus 1, looking like this. Here's the value of 2. What we're looking for is the tangent line at that spot right here. What is the tangent line? Just the slope of that spot right there. So to do this, we do the limit as x approaches 2 of f of x minus f of 2 over x minus 2. What happened there? Come on, computer. Work with me here. I should say this isn't b, I should say this is x. F of x minus f of a over x minus a. So we're going to use our equation, this equation here. We're going to use this equation. I have f of x minus f of 2, my value I want, over x minus 2. And slowly what we're going to do is we're going to say, here's some x. We're going to take this x, and we're going to get closer and closer to 2. We're going to do a limit as x approaches 2 of this value. Right? This x over here, this x right here in the beginning and the end of the equation is going to get very, very close to 2. And as we get closer, right, this is just the formula for slope. Our slope is going to get more and more exact until it is equal to this one particular spot at 2. How do we do this? It's just like solving a limit. F of x, well, that's x squared plus 1. Put your equations in there. Minus f of 2, that's 2 squared plus 1. Over x minus 2. Okay? Nothing too crazy right now. Right? Nothing too crazy? F of x minus f of a over x minus a. This formula here, right? You plug in your equation, leave your equation the same, minus the value you're looking for, right? Leave the equation, minus you plug it in. Leave the x, minus you plug it in. Equation minus plug in, equation minus plug in. And then we are eventually going to find a limit. If I plug it in now, what's going to happen? If I plug in my 2 right now, I'm going to get 0 over 0. So I know that I have to do a little bit of limit manipulation, just like you did before. So this is going to be the limit as x approaches 2 of x squared plus 1 minus 2 squared is 4. 4 plus 1 is 5 over x minus 2. I'm solving this equation. As x approaches 2. When I reduce this upper part, I'm going to get x squared minus 4 over x minus 2. Oh. That's interesting. Right, so all I've done is I've taken my formula that I had, minus it from the one I want. I wanted it 2, so I plug a 2 in there, over x minus 2. Take the equation I want, minus the spot I want it at. Simplify my top part, and I get this equation here. What can we do to this? Right, we're solving a limit, everybody. What can we do to this to solve this limit? How do I solve this limit? What am I going to need to do? What little mathy trick can I do to simplify this? Anyone have any idea? Again, if I plug in a 2, it's going to be 4 minus 4 over 2 minus 2. It's going to be 0 over 0. The factoring thingy, yes, exactly. Look at this top, x squared minus 4. That is a perfect difference of squares. So I'm going to have the limit as x approaches 2 of x plus 2 times x minus 2 over x minus 2. And I can cancel out. Cancel, cancel. And now that I've canceled those out, I can plug in my 2 to the x plus 2, right? Limit as x approaches 2 of x plus 2. Oh, God. So messy, everybody. The limit as x approaches 2 of x plus 2. And that's just going to be 2 plus 2, which is 4. And that is my instantaneous slope. This is the slope of the tangent line. Slope this is the slope of the tangent line. I'll write this better. My instantaneous rate of change. Found by using the limits, found by taking the limit as x approaches 2 of my formula here. Right? The formula was the formula for the rate of change formula is the limit as x approaches whatever value I want, a, right, of f of x minus f of a over x minus a. For instantaneous rate of change. The slope of the tangent line is equal to the limit as x approaches some number, right? Whatever number we want, that's the instantaneous rate of change. And when we do the limit, we're going to use the tools we had before where we do some simplifying, we break it down, we get our equation, and we get that limit that lets us find the slope at that point. Lets us find the slope at that instantaneous. Should we do one more example? Do we have time? I got less than 4 minutes. What I'm going to have you do for your homework assignment over the next day is practice finding instantaneous rates of change and practice finding average rates of change. Okay? Your homework is going to be practicing finding these instantaneous and average rates of change. Let me look this. I had posted something up on Schoology. Yes, this is what I would like you to do. So your homework is on Schoology. It's a PDF. It's a file that I've attached to the work, to the assignment rather. Homework on Schoology. Try those questions out. I think there's like maybe 10 questions. Finding the average rate of change and finding the instantaneous rate of change. Okay. Let me open it up. Posted it, but let me publish it. Let me show you now where this is here on Schoology.